And having started it, I will welcome you to the Monday seminar. Hi, everyone. I'm Chris Marone. I'm super excited to see you. And I'm really happy that Kayla Kroll has put together a talk for us. We owe a lot to Kayla and for spending time to do this and for agreeing to give a talk in an online mode, which isn't really everyone's favorite, but it does provide an interesting opportunity for us. And in particular, if you're new to this seminar series, we have a nice long discussion and question and answer period at the end. So please plan to join that, and this will be right after the talk. And our normal mode of operation is to ask you to mute yourself, but to encourage you to unmute and ask points of clarification along the way in an interactive style. And then, but to save, real questions until the end. So I will turn things over to Kayla. Thank you very much, Kayla, for putting this together. And please go ahead.
Thanks, Chris, and thanks for the invitation and all for being here today. Today we're going to talk a little bit about forecasting induced earthquakes with the ORION toolkit. ORION we'll get into quite a bit in detail in the talk, but was funded out of two programs from the Department of Energy's Fossil Energy and Carbon Management Office. These programs are called the SMART Initiative and the National Risk Assessment Partnership. So NRAP is on its 13th year currently, and they were really charged with identifying the risks associated with carbon storage and then developing what we call ROMs or reduced order models to address those risks. And so a reduced order model is really meant to be this sort of lightweight, user-friendly tool that can help operators address a certain risk at a site. So they have a number of different toolkits, lots of ideas for reservoir modeling, for example, for wellbore integrity, things like that. And the task that I lead is focused on induced seismicity. And within that, we do two things. We do the high fidelity modeling of earthquake sequences, for example, to look at how changing in some mechanism or some operational parameter impacts seismic sequences. But we also develop ORION, which is this sort of reduced order model for forecasting induced earthquakes. And then within the SMART initiative, this program was stood up about 5 years ago, and that was really built towards developing front-end user-friendly tools with visualization capabilities to help operators make decisions in real time in all types of subsurface applications, but with an emphasis on carbon storage. So both of these projects came together to help support ORION, which means that we have a nice robust backend or computational infrastructure. And then we also have some really good visualization capabilities that have now been separated off of the tool and are available in the open source domain for any developer that wants to use an interactive and sort of easy to interface with GUI system. So we'll go over both of those aspects today. As soon as I can figure out how to advance my screen. Okay, so just real quick, ORION itself stands for the Operational Forecasting of Induced Seismicity. The tool it's built to be open source, and so we have a very transparent licensing structure. This is licensed with an MIT license, which means that it's completely permissible for co-developers to develop on and include in various workflows. And it makes the science behind what we're doing very accessible to anybody who's interested. The tool itself is an operationally driven ensemble forecast. So what that means is that we generate a number of different forecasts and then aggregate them in an ensemble. And it's meant to address induced seismicity related to all types of operations. And we'll get into that in a little bit more, in the next slide or two. And finally, the ultimate goal with the toolkit is to provide operators and various other stakeholders with actionable and proactive metrics to help them mitigate induced seismicity at their site and point of interest. And so by now we're probably all familiar with this really great figure that shows that induced seismicity is really ubiquitous across all different types of subsurface operations where fluid is injected or extracted from the ground. And so we see a lot of induced seismicity associated with hydrocarbon storage and production, with shale gas exploitation, although this is a slightly different mechanism leading to it oftentimes, with geothermal operations, various mining operations. And then for the purposes of this talk, we'll really focus on the wastewater disposal induced seismicity. That's rather similar in mechanism to the properties and the situations that lead to induced seismicity in carbon storage sites as well. And what we've seen in the central and eastern US is that seismicity rates have really dramatically increased over the last 40 years or so, and primarily driven by the increase in seismic activity related to these types of operations. So if we just look at the seismicity in the central and eastern US and then focus in on the areas of active oil and gas operation or wastewater disposal, we see that there's been an increase in the rate of seismic activity from like about 200 events per year in the early 2000s to almost 650 events per year, magnitude greater than 3 in the 2010 period or so. And that has reduced a little bit, maybe down to about 400 events per year, but is still quite high relative to the background rates. And what we have also seen is that there's been a number of magnitude larger than 4 events, and maybe even sometimes magnitude 5 events associated with wastewater disposal and hydraulic fracturing activities in the Texas and Oklahoma area in particular. And so the USGS, back in their 2018 release of the National Seismic Hazard Map, did decide to include the seismic hazard related to induced seismicity in this region in Oklahoma. But in the most recent iteration, in the 2024 release, they've decided to take the induced seismicity components out for 2 primary reasons. One is because of the transient nature of induced earthquakes and how they're tied to the various types of operations that are being conducted in these areas in the central and eastern US. And so again, if we just overlay those areas of active operation on top of that hazard map, we see that there's relatively low hazard in places like the Permian Basin, where there's been, in fact, just last week, another magnitude 4.5 or larger event due to oil and gas activities and wastewater disposal in this region. Additionally, there's another type of feature to consider. So these hazard maps are static. They're 1-year productions. And these, in general, the operators in these types of areas might be actually interested in sort of a more real-time or a tool that offered some sort of management strategy, for example. So that is to say that if there's a hazard or a probability of a certain magnitude event occurring, the operators might like to receive some information that says that the probability of said event has increased, and then the tool might be able to give them some sort of actionable metric, like reducing the injection rate in one well or a set of wells to reduce the likelihood that that earthquake might occur. So with Orion, we're really trying to take the fundamental physics that goes in and underlies things like the National Hazard Map and additional types of induced seismicity forecasting tools and expand them into a toolkit that actually provides access to these sort of advanced technical processes and makes it delivers it in a user-friendly way. And as I mentioned before, there's, different kinds of stakeholders involved in this. So of course there are the operators and the regulators, but then there are other types of interested parties. So for example, the public or just the residents of these areas might be interested in why they're feeling events, earthquakes in regions where they haven't been, where they're not used to those types of events. We have different types of insurance companies or risk management companies that might also be interested in the seismic hazard at the site and or the risk associated with it. And then we have various interstitial companies that sort of link maybe say the operators to the academics, for example. And those are your seismic service companies or institutions that are go out into the field, install seismic instruments, deliver seismic catalogs, and then also could potentially provide a hazard forecasting or seismicity forecasting service to the operators and the regulators. The interesting thing about all of these stakeholders, though, is that they both have different access to data, and they also have a different set of fundamental expertise. So we have, in the academic sector, PhD level experts in reservoir modeling and earthquake physics, for example. Some of your your oil majors might have some in-house representatives that are experts in those areas as well. And then, of course, like your service companies would have PhD level seismologists, for example. But not all of your independents, and certainly not the regulators and smaller operators would have access to these types of expertise. So Orion is really geared towards trying to address the needs and the data accessibility that all of these end users have. And just to take this classical workflow that's required to forecast seismic events and to sort of break that down into the components that Orion does in internally and those that it relies on for both input information and for output or further analyses. I'm just going to again use this really lovely workflow figure and highlight some areas. So in particular, this yellow box indicates the inputs that we have required to generate a forecast in Orion. So if we have injection into the subsurface and then migration of fluids, they either interact with faults and generate earthquakes related to the direct pore fluid pressure effects, or they cause some volumetric change in the stress field and generate earthquakes with respect to the poroelastic components of the in relation to the injection operation. These would be considered an input source. So we would compute the pressure changes and stress changes externally to Orion and provide that as an input. Another type of input is going to be your seismic catalog. We accept both high fidelity catalogs and just general catalogs that are produced by the USGS, say their Comcat catalog, for example. And then we incorporate all of these things and use them to generate a forecast, which captures basically this part of the workflow within the Orion tool itself. The one thing that we don't actually include, so I should have modified the box a little bit for the purposes of this talk, is ground motion prediction equations. So the Orion tool actually stops at the seismic hazard and doesn't actually include risk. And right now it doesn't have any components of ground motions, primarily because the forecasts that we're generating are for locations where events magnitudes have been relatively small to date. As I did mention, there are some induced events that are magnitude 4 or 5 for which we do have GMPEs, but those are not quite yet incorporated. That's work in the next year. As I mentioned, also Orion really does stop at the seismic hazard calculation. So we are producing magnitude probabilities of exceeding a certain tolerance magnitude. But you can imagine that you can take that output and you could pipe that to an insurance or risk management company who would do the full risk calculation. Okay, so looking a little bit deeper into the different types of input data requirements. The Orion requires two input data types, a pressure model or a stress model or both, and then also a seismic catalog. So for the pressure model, we have a couple of different options for providing and uploading pressure models. The first is that if a pressure model doesn't exist, then you can calculate, oops, that's the second bullet. You can upload the injection information. So this would be your well location and injection rates over time. And we would use a built-in analytic solution for pressure as a function of space and time in a homogeneous half space. And so if you have absolutely zero information, but you do have access to, let's say, a public repository of injection rates, and you can upload that to Orion and it would calculate pressure in space and time. And we have an example of something like that. This is the pressure history at the Illinois Basin Decatur project. But this pressure history actually was generated with a high fidelity reservoir simulator using the tough FLAC workflow. This was calculated by LBNL. And you can upload that pre-calculated pressure table in HDF5 format or any of the various types of proprietary data formats coming from your commercial reservoir simulators like COMSOL, CMG, etc. And you can upload either of these to Orion and it will use that information to help generate a seismic forecast. I will say that in the current iteration, we are focusing only on the direct pore fluid pressure impacts on induced seismicity. But in our upcoming work within the next year, we are expanding the calculations to include full pore elasticity. And the second piece of information that's required is a seismic catalog. So Orion again accepts two different types of input. So one is the high fidelity catalog that might be computed by, say, an academic institution, or the USGS, for example, is Comcat catalog. In a separate project that's independent to Orion, but still within the DOE portfolio, Livermore, my group at Livermore has partnered with the company, the service company called ISTE, to apply machine learning based tools to generate real-time catalogs of induced earthquakes in the various sites, say in West Texas, and then to produce real-time forecasts of induced seismicity related to those catalogs. So this is a project that we're calling Reconnect. It just started this month and will be able to produce real-time forecasts of induced seismicity for ISTE's clients and wherever those clients reside. And then so we use the pressure history and the seismic catalog and the properties of the seismic catalog to generate a forecast. And the forecast, as I mentioned before, is something, it's an ensemble-based forecast. And the way that we generate the ensemble currently is by being very agnostic about which type of forecasting models that we use. So if we look into the earthquake forecasting community, there are traditionally two sort of bins of different types of forecast models. We have a couple of different statistical based models and even some that aren't included here. And then we have various flavors of your so-called physics-based models. So these are the sort of classic rate and state type of earthquake forecast or rate models. If we were to take the calculations from either the statistical forecast method or the physics-based forecast method and compare them to an observed catalog, so that would be this black line here. This is from data from New Zealand. We see that in some cases, the statistical models behave either really well or rather poorly, and the same can be said for the physics-based models. And this has a lot to do with the amount of complexity that is incorporated in both the statistical and physics-based models. And when you are trying to generate a forecast for induced earthquakes in areas where you have relatively low background seismicity, it actually makes it quite difficult to generate a stable and a high fidelity forecast. So what we've decided is that instead of trying to separate out which of these forecasting methods are better, so to speak, we've just incorporated them all, and have then generated a number of different types of forecasts, calculated the misfit or how well the forecast is able to reproduce the observations, and then use some weighted approach to aggregate the models together based on their goodness of fit to the previous data, and then use that to generate this forward ensemble sort of approach or ensemble forecast. That means that the ensemble is really tied to the forecasts that are better able to capture the observed seismicity. So those would be more heavily weighted than the forecasts that are pretty poorly fitting the observed seismicity like these, which would be rather lowly weighted in the ensemble. Looking just a little bit further into some of the equations, those of you on the call who are familiar with this work know these equations quite well. We've separated these again into this sort of physics-based category and the statistics-based category. And for the physics-based models, we're using two different types of approximations. One is the so-called coupled Coulomb rate and state model that does actually include both co-seismic impacts of impacts on the seismicity rate change, and then is able to predict or forecast rather the rates in the interseismic period. And then there's a relatively new implementation of the traditional rate and state equations that applies to sort of declustered catalogs, which means that this is sort of applicable in this sort of interseismic period because we're taking out all of the co-seismic impacts on the rate change and we're removing those. In the statistical framework, we have that kind of falls into two categories. We have this sort of traditional ETOS model, which does take into account parent-child events and is able to capture some earthquake clustering. And then the seismogenic index model, which just is basically a simple Gutenberg-Richter implementation that adds a component of the related to the injection operation. One of the things that we've done for all of these models to make them consistent is you'll see different stressing rate terms here. We have cast in this case, the pressurization rate in terms of the full Coulomb stressing rate and employed that in all of the different types of forecasting methods, so that the sort of pressurization rate, that term can go to zero, but the Coulomb stressing rate will never go to zero. And then also starting and developing the code in general based on this equation allows us to more easily incorporate poroelasticity when we get to that stage as well. And then, as I did mention before, some of the models are able to include earthquake clustering. So that would be your sort of physics-based model that includes earthquake clustering and this term. And in ETAS also, we're able to account for some of the clustering impacts. And so that would be your sort of secondary triggering, or the instances where the sort of seismicity rate is increased due to stress changes from a nearby earthquake. And looking at the implementation of some of these types of models, this is an example from the Illinois Basin Decatur project, which we'll see quite a bit coming up. But what we wanted to show here is just the pressure history in space and time, along with the seismic activity that occurred at that site. And then in this figure here, we're showing the number of events that have occurred as a function of time. This is the number of events is given by the black line. The dots are the magnitudes of those events, which are all relatively small, all like smaller than 1.5 or so. And then here is in the blue in this figure is the pressure history related to injection of CO2 at the Illinois Basin Decatur project. So these are basically the two different types of inputs that we use to generate forecasts within Orion. Here's an example of a seismogenic index model. And this is example of one implementation of a rate and state model. And then at every time period during the training, we calculate the misfit and then save the model parameters and use those to produce a forecast, but only in situations where the misfit has been reduced. And this is one of the ways in which we ensure a low uncertainty or lower uncertainty in the forecasting period, and that allows us to move forward to real time. One of the types of work that we're working on, so this is some machine learning based forecast that was generated by our colleague at the University of Madrid, Linus Walter. And what he's doing is basically separating the observed data, so this would be your seismic catalog information and the modeled pressure information, into a training window and a testing window, but these are very small and overlapping windows, say about 10 days each. And he's able to use a random forest model to generate a seismicity forecast and a forecast of maximum event magnitudes through this machine learning based approach. One of the nice things about a random forest model is it actually is able to capture what types of input information or input features are most relevant to the producing the output feature, which would in this case would be the seismicity rate. And what we find is that the pressurization rate in at least in the early time periods is most impactful on producing a seismic forecast. But then when more seismic data is gathered, it actually the seismicity rates themselves, or the observed past seismic record, is most influential in producing the seismic forecast. So in addition to the two types of traditional seismic forecasting workflows that we are incorporating, so that would be your physics-based forecast and your statistical-based forecast, we are also working on incorporating various types of machine learning-based forecast into the ensemble as well. And as I mentioned before, so now we've seen basically 4 or 5 different types of forecasting approaches, all with various levels of confidence and all with different predictions. And we are aggregating those into an ensemble forecast, which is very similar to the way that, say, hurricane track forecasting works. And one of the key features of this is that it actually also allows us to address the uncertainty, both in the input parameter space and then the uncertainty with respect to the model outputs. So this is an example of a time-dependent forecast. And so the seismicity rates here, I think, are in white, the observations, and then each of these colored lines is a different type of forecasting model applied to that same data set. And we do have methodology for visualizing the uncertainties surrounding this, but it very much appears like in this case with probability density functions of your sort of input and your output features. Okay, and real quick before we get to what a case study that's actually computed within Orion and what Orion, the infrastructure looks like, I just wanted to make a note about the code structure. So we have organized Orion as a pure Python and pip installable package, which you can download from this Get repository. It's organized as a series of submodules that contain tools for managing the data, the forecast, the visualization, and the pressure models, for example. And the code and structure guidelines is we're adopting pretty rigid coding standards here. So we are using the PEP 8 standards, which are enforced by the YAP-F tool. We have some pretty strict rules for developers. So, for example, we're taking advantage of the Python functionality and modern coding languages, which means that all of the variables, for example, are expected to be human readable to make it easier for new developers to implement a forecast. And then we are implementing modern object-oriented coding practices. So that means that we have things like classes, functions, methods, etc. And we also include the Google formatted docstring, which helps with the documentation. So we do have a living documentation page that's written in this sort of RST format and is built on the fly using the Sphinx package within Python. The documentation is hosted here. And as you can see in the documentation page, if you were to go to that, we have a user guide, a set of examples for various types of data formats. And then we also have a developer guide. So as I mentioned early on in the talk, we have taken some pretty, uh, well, some purposeful measures to make sure that Orion is very transparent and can be used and accessed by all types of developers, and various types of developers can either take the code and implement it into a workflow or develop a workflow that can be back incorporated into Orion. And the developer guide here shows the list of information that one needs to be able to develop a component of Orion and build it back into the Git repo. Okay, so from here on, we will look at an example of applying Orion to a case study. So the case study I've referenced a number of times is the Illinois Basin Decatur project. This was a CO2 storage demonstration site in Decatur, Illinois. Um, we're using this site because it's got a actually rather comprehensive data set associated with it. We do have the microseismic event catalogs, and we also have a couple of different types of reservoir models that were generated for pressure migration in the subsurface for this location. And then the graphics here are so if you were to go to that Get page today, download Orion, you would install basically a desktop-based GUI interface that looks a little bit different than this. This would be our 2.0 release, and this is built on the Plotly Dash package from that exists within Python. And this is the front end or the graphical interface here is a package that we hope to release in the next month or so called Strive. So what we did with Strive was, I mentioned this earlier on, was we basically just took the graphical and the visualization components of our GUI-based desktop interface, separated those two things, the back end that computes the forecast and the front end that computes the graphics and the maps and the visualizations, and package the front end capabilities into the Strive package, which you're seeing here. But that is also an MIT open source license that allows different types of developers to plug in their workflows into a nice interface that's rather user friendly and has a nice look and feel to it. And it helps have a sort of consistency across the tools that we're developing in the smart platform and various other types of workflows. And so we've shared the Strive package with end users at our operational partners and with our partners at the service companies as well. So if anybody's interested in generating graphics like this, it's also available for use. Okay, so going back to the actual science here. There are on the seismic catalog tab of the Orion interface now, we see a variety of plots. So this would be just a map view of the event locations as a function of time. So in each dot here represents a seismic event. The size of it is scaled by the event magnitude, and it's colored by the time since the operation began. On a separate plot here, this is the event magnitudes as a function of time. Each of these is again is an earthquake. In this case, it's actually colored by the depth. And so we can see the magnitude sort of decrease with time, and the depth stay like relatively constant, in this case, below the reservoir for the most part. We also see some statistical features that are important for calculating the forecasts. So this is just your traditional Gutenberg-Richter plot, and this was b-value evolution as a function of time. I will say that in keeping with our sort of agnostic approach for any of the types of forecasts, we also employ this type of approach for all the different types of reservoir models and computation of statistical parameters. So, for example, there's 2 or 3 classical methods for calculating b-value, and a sort of newer approach that was presented recently by Nicholas van der Elst, the sort of b-positive method. When there's multiple ways of calculating a parameter, we've employed all of the ways and then generate a forecast on whatever that method returns, or the value that that method returns. And so for b-value, I think we have 4 built-in methods. For magnitude of completeness, I think we use 2 or 3 different built-in methods. For things like declustering, we do use the 3 traditional types of declustering methods. So the Gardner-Knopf, Riesenberg, and Jones, and the nearest neighbor approach as well. And so just to reiterate, every time there's multiple methods for calculating a parameter, we will calculate that parameter with all the methods and then generate a forecast from whatever that parameter value returns. So any forecast that just requires a b-value, for example, like the seismogenic index model, if we have 4 different values of the b-value, then we have 4 different forecasts. So that helps us address the uncertainty in the forecasting space as well. Stepping through a little bit further, we have another tab that shows the 3D overview. This is a relatively simplified image now, but you can imagine that. So here we're just looking at the seismic events with depth. The green lines are the well locations, and I didn't actually make this interactive, but if I had done that, you can go to the legend and click any of these features to turn them on or off. So they're added as various layers. And if you were in a situation where you had a complex 3D block model, say representing the geology or the velocity structure or whichever feature that you were interested in, it can be added to a plot like this with the well locations and the seismic events layered on top of that. And you can interact with this in 3D and rotate it and all of those kinds of things. Moving forward to the portion that calculates either the pressurization rates or based on an input pressure file or based on the injection rates, we do have a number of other tabs there to represent that data. So in this case, this is the injection rate from the injection well as a function of time since the operation began. And then beneath that, we have the cumulative volume injected at the site. As I mentioned, this is just a relatively simple example with one injection well, but we're able to represent the injection rates from all wells in this panel, and then the cumulative volume across all wells as well as if you were to say maybe go to Oklahoma or to the Permian Basin, for example, where you have thousands of wells operating at one time. I should mention that though this injection rate field here will only populate if an injection rate is uploaded. If you upload instead a pressurization map, then you will not get any injection rate information for individual wells. Okay, and so if we look forward to how those 2 different types of information are visualized and how we compute a forecast, we have a pressure tab here that in this case shows the pressurization rate as a function of space. What I'm not showing is off the side of the map here. There's a time slider, so you can change the 2D slice in the image here that's shown as a function of time through the injection operation. Again, you can click on each of the individual layers in the legend, and you can turn on and off, like say, the well locations or the seismic data. And then what's also not shown on the outside of this panel here is the ability to toggle between pressure change and pressurization rate. We show the pressurization rate because that is the parameter that's important for the forecasting, but lots of your reservoir engineering colleagues like to see the pressure change or the overpressure, so that's output as well. And we use that information along with the pressurization rate, along with the other information presented on the other tabs to compute an ensemble forecast. So on this page here, I'm showing the number of events per year per grid cell. We have subdivided in order to produce a spatial forecast like this on a relatively small scale. We do subdivide the region into grids. The grids in this case are 200 meters, and we have done lots of work to understand the sensitivity of the grid size. You might expect that the seismic forecasts, especially those that are tied to the cumulative number of events in a grid cell, are very, very sensitive to the grid cell size, and that is very true. We do take some steps to ensure that the impact of the grid size is minimized. And we have the results of the sensitivity analysis basically suggest that we should not be using a grid size that's smaller than, say, 200 meters or so. But by comparison, if we were to look at the CSEP type forecast, they use a 0.1 degree grid size for larger spatial reasons. Larger spatial regions, which is, I think, more reasonable when you go to larger areas. But you can see that this is a relatively small site, and the uncertainty in the forecast is reasonably small given the spatial resolution that we have. And I should also mention what's also not shown on this figure and outside the bounds of this box, similar to how you can toggle between different layers on the pressurization tab, between pressurization rate and pressure change. Here you can toggle between the seismicity rate forecast, the cumulative number of event forecast, or the probability of exceeding a target magnitude. Um, and I did mention several times now that the Orion is producing an ensemble seismicity rate. And so I thought for completeness, we would show the different attributes of the component forecast that we're using. So this is one example of a statistical forecast. That's your seismogenic index forecast. This is the rate and state ordinary differential equation forecast. This is based off of Siegel and Liu. This SAFE model is a machine learning implementation of the Coulomb rate and state model that uses PyTorch capabilities to produce a fast model fit to the observed data. And then this is a spatially varying Coulomb rate and state model. And as I mentioned earlier on, you can see that some of the forecasts look completely different, and some fit the observed data better than others. And the ensemble is the weighted sum of all of the component forecasts, and it looks like this. Looking at the sort of 1D forecast or the temporal evolution of seismic activity at the same site. So in this case, the catalog data, it's actually kind of hard to see here, but it's in the dark blue line here that my cursor is going over. And each of these are the component forecasts. And then this would be on the bottom panel here would be the uncertainty associated with each of those component forecasts. So these are more, well, we're showing it in these as the shaded regions, but these are basically your error bars with a 95 and at the 2 sigma confidence interval. One of the other key things about Orion, I think, is this page here, which shows the pseudo sort of traffic light information. And I call it a pseudo traffic light because the traffic light protocol is historically been defined based on an event that has occurred in the past. And so it's purely retrospective. In this workflow, we've tried to sort of flip that on its head and make it more prospective and proactive in the sense that an operator would then be able to act on a proactive metric, for example. So we have afforded a lot of latitude here for the end user to engage with the traffic light. And this is really due to the trying to accommodate the different types of risk tolerances and different types of regulation that one might encounter in various areas. So, for example, what we're showing here is the magnitude, or I'm sorry, the probability that there will be an event larger than magnitude 2 within the next 100 days. And that's a relatively low. It's a sort of 9 or 10% probability that there's going to be a magnitude larger than 2 within the next 100 days. Um, However, one might take issue with the sort of static value of the magnitude and then also the forecasting duration. So these are variables that are allowed to be updated by the end user. And so, for example, in some parts of Texas, depending on the type of operation, an operator is required to take action at magnitude 1.5. And that would be a 1.5 that has occurred. But we might be interested in a 1.5 occurring in the next week or the next month. And so we can update the interface to address whether the sort of threshold magnitude and the target forecasting period. And if we do that and say, hey, we're actually now interested in what the probability of exceeding a magnitude 1 is in the next 100 days, we can input that and then it would return this figure, which basically says that there's like a 75% chance or higher of generating a magnitude 1 in the next 100 days. I should also mention on this figure here that the color scale, so the green indicates a sort of continue as with business as usual. The yellow is an area where if the probability falls in that range, it might, warrant some caution on the operator's behalf. And the red is really to indicate that an action should be taken. Where these, like the cutoff threshold, those can also be tailored to the various risk tolerances for an operation, a particular operator, or even like say the regulation. So where possible and where these values have been defined for say like the magnitude, we're pulling those from local sources, and this is easy to do in states and in regions where there is a regulation. We've made this really open and allowed a lot of flexibility here because the regulations in lots of cases are not set, and certainly not with respect to carbon storage in the US. So there's, like I said, there's a lot of flexibility allowed in these plots, and that's why, and it's all purely prospective. So it's a probability of exceeding a magnitude event in the future and not retrospective looking at events that have already occurred. In a situation where the probability falls in the red bin, a message will pop up that says the probability of exceeding a seismic event that you've entered is now greater than your risk tolerance or your threshold upon which you want to take action in your forecasting period. And then if you were to click on this message, it opens up an additional tab on the interface that's called operational management. This is not fully fleshed out yet, but what we've done here is we've taken some management step, in this case, reducing the injection rates by a factor of 2 that causes, say, a 50% reduction in the pressure. And then we're recalculating what the probability of exceeding a magnitude 1 would be in the same forecasting period. So we see that reducing your injection rates by a factor of 2 reduces the probability from about 77% to about 57%. And in this case, this is an operational metric that can be employed by the operator to sort of reduce the likelihood that they're going to be generating a seismic event. Okay, so that sort of concludes our example related to the Illinois Basin Decatur project. And what we're going to focus on now is just some other forecasts and some other areas where we've employed Orion. So this is a pressure model that was provided by Katie Smee at the from Scissor in the Texas BEG. So what they had done in this work, it was published last year, was they took all of the injection wells in West Texas. They gridded up the sort of larger region, used the CMG reservoir simulator and generated time-dependent maps of the pressurization change, pressure change in space, and like I said, in time as well, from 1983 through the end of 2023, I think. Sorry, I think it's the end of 2020, the end of January 2023. We worked with them and were able to export depth slices of the pressure change as for every time step and incorporated those into Orion. And then we calculated the seismic forecast in Orion for the injection information. So what you can see here, this is just a map view of the pressurization rate in Orion that's related to the pressure change that's shown in their CMG calculation. And these are all of the events that have been occurring in the West Texas area since maybe 2015 or so. And what we can see is, and it's I think reasonable, but the pressurization rates are highest in the area where you have high pressure change and also where most of the well activity, injection activity is occurring, which is well to the north of where most of the seismic events are occurring. And so if we were to take that one step further and we're to calculate the each of the component forecasts based on that pressurization rate map, you'll see some things that you might suspect. One, that the seismogenic index model, which is really tied more to the locations of high seismicity rate rather than to the locations of high pressurization rate, that tends to show that the seismic hazard is highest where the earthquakes are occurring. And our two physics-based models, which are really tied very closely to the pressurization rate input, you see that the seismic hazard in those areas is really higher where the pressurization rates are higher. And this is one of the benefits of the ensemble modeling, because when you incorporate all three of these, you get a map that looks like this, which shows an area of high seismicity rate in an area where we're not actually experiencing seismicity, but there is a high pressurization rate. And you do have a higher seismicity rate in the area where the events are occurring. And then if we were to look at the cumulative number of events with time, we see that there's a decent fit. In this case, the catalog data is in white, and then all of the colors are the various component forecasts, and they do a reasonably decent job at fitting the data. And for this case, this is a relatively old example. I think I computed this forecast in say February of last year, and at the time there was maybe almost a 60% chance that there was going to be a magnitude 5 in the next 100 days, and there was indeed a magnitude 4.7 and then a magnitude 4.2 very shortly after this forecast was calculated. So this was again done January 31st was the end of the pressure history, and these two events occurred 3 weeks later. And then moving forward to one last application, this is the carbon storage site in Alberta, Canada at the Quest site. This is operated by Shell. This data is, or this example is drawn purely on public data sets. So this is a map of the seismic activity at the site. And included in this report is an injection history for each of the 3 wells given these stars. These are images from the sort of legacy version of the Orion interface, but it shows the magnitude as a function of time, and then the injection rate at each of those 3 wells. We've chosen to take some smoothing steps here to smooth out the high frequency information in the injection rate. And then we've computed a pressurization rate model for the injection here using the built-in Tice equation for pressure in space and time. And so what we get is a map that looks like this, as it's relatively simple because it's injection into a homogeneous reservoir. From this pressure and pressurization rate map, we are generating probability of exceedance maps that look something like this for this area. And again, this is our temporal forecast with the with the catalog data in white and the different component forecasts in the colors. In this case, the traffic light protocol here was set to produce a probability for a magnitude larger than 1.5 occurring in 100 days. And we see there's about a 65% chance after this forecast was generated. And in April of 2023, so this, I think, forecast was done in January of 2023, there was a magnitude 2.4 that occurred sort of right out here from this map area. Okay, so I had talked along the way a bit about the future developments in Orion. The first and I think the most pressing feature would be to incorporate faults and fractures, which would then allow us to estimate the forecasts using full mechanical implementation. Right now, we're taking the approach of Dietrich 94, where we're calculating the seismicity rates due to a population of nucleation sources within each grid cell. So in that way, you're sort of assuming optimally oriented faults, and it's a point source for event rates. Once we start to incorporate faults and fractures, then we can calculate the mechanical stress changes on those features themselves and calculate the event rates associated with particular structures. We started with the sort of lower level implementation only because in lots of cases of induced seismicity, we've noticed that lots of the events occur on faults that are not previously mapped. And you really have to rely on the microseismic or the seismic data to interpret fault structures. So, and this I think remains true for lots of new either greenfield sites or sites with a lack of previous seismic activity. So we wanted to be able to address and compute a seismic forecast in those areas, but without maybe necessitating the need for previously identified faults. One of the next features that we want to incorporate is ground motions and sort of focal mechanism data. The ground motions are important for the larger magnitude events, say 4 or larger, but we're working on an implementation of calculating GMPEs at the local scale for magnitude 2 events, and then we'll start to incorporate the ground motion estimates from any of the target magnitude event in the in the interface as well. One of the key features of moving towards operational management and suggesting changes to your operation, changes to your injection rate, for example, those have techno-economic impacts. So if you have a certain volume of fluid that you're trying to inject over a certain amount of time, reducing your injection rate is going to increase the length of time that you need to inject, which is going to cost more. So we want to also do is pair or couple our seismic forecast with a techno-economic analysis to give an operator an understanding of, if we take this operational management step, this is how much it's going to cost. And so they can incorporate both types of information, both the seismic data and the hazard forecast and the economic costs associated with an operational management step into their decision making. We did talk a smidge about the uncertainty quantification and sort of air propagation through the analysis. We do present these results in some capacity. They're just not the most easy to understand for, say, the public or a regulator or somebody that's not so familiar with reading joint PDFs. So we were working on methods to incorporate more easily to understand visualizations of the uncertainty associated with each of the forecasts. And then finally, and I think this is probably a larger challenge, is trying to understand and employ the forecasts in areas where you have multiple types of sort of co-located operations and maybe even stacked operations. So what this means in the real world, and the Permian Basin is a really good example of this, the operators there are hydraulically fracturing for oil production in a reservoir that is actually deeper than the injection reservoir for wastewater disposal. And those two different types of operations are obviously interacting in some way. And so taking into account both of those operations, I think is important. And then if you start to add an additional operation like large scale carbon storage to that in that basin, it's going to be important to incorporate the impacts of all of the types of operations. And then finally, the last thing to think about here is that we have operators of various sizes. So the Permian, again, is a good example where Exxon is operating, Chevron is working out there. And then we have some smaller oil and gas companies as well. And, one of the operators might have 1,000 wells versus another operator that's in the same basin, but they only operate maybe 5 wells. And even within the sort of say 1,000 wells that Exxon operates, some of those wells are connected at the surface via pipeline, making it easier to transition fluid away from one well to a different well as an operational step or management step, for example. But we don't know currently which of those wells are connected and which of those wells are not connected. So offering different management solutions like partitioning fluid between two wells or reducing the rate in one well and piping all the fluid to a different well, one, those have economic costs associated with them, and two, they are perhaps easier to target in some cases than in others. And so, and for this, in this regard, we really have to be working with the operators very closely to understand the types of connectivity between the wells and the different types of management steps that would be advantageous for them, both for managing the fluid and then also managing the seismic activity. And with that, I'll just say thank you and take questions.
Okay. Oh, thanks a lot. That was great. Great, Kayla. I will invite people to unmute, turn your camera on, do what you like. Join me in thanking Kayla for a really nicely put together talk and like perfectly on time. You are ready to go to Switzerland next week. You got the timing done perfectly. Yeah, it's really nice. And okay, while we give Kayla just a second to catch her breath, I will invite you to use the raise hand feature at the bottom of your screen. It looks like that. I guess you're all experts, but maybe not. Bottom of my screen, there is a feature that looks like that. That'll put us in order to ask questions and to start a discussion. And while you are all thinking about what you'd like to ask, I will ask a quick question about, when you need a seismic catalog to go into this, Kayla. So what do you do in a place where you're just starting and you don't really have much of a seismic catalog yet?
Yeah, that's a great question. And uh, happy to hear other solutions for this. So one,